Hi friends, welcome to lecture 55 of my helicopter dynamics class. And today I'm going to discuss the blade flapping equation in forward flight. So we are going to use the expressions we have derived using blade element theory, put it on the right hand side of the equation and expand it out. I'm Dr. Ranjan Ganguly. So let's think back about the equation for the flapping blade. So you will recall the equation here, beta double star plus beta is gamma m beta bar. Now, what changes now in forward flight is that this m beta bar needs to be calculated, and to keep things simple, we assume the blade is such that there is no offset of the hinge, so nu beta is 1. So let's look at the term involving gamma m beta bar. So this is given by the expression which involves Fz, and so I can write m beta bar in this manner. I take the gamma down here. Remember, gamma is rho ACR4 by IB. Simplify this expression, so we get this expression here. And then we introduce what are the things inside Fc. So essentially from BET, we now know the expression for Fc. That's in terms of rho AC, UT, UP, and theta. Okay, so that's the main discovery we have made using BET, which we can now bring into the equation for m beta bar. And this is very important because this will now let us get a closed form expression for the flapping moment. So now we need all the components which are there inside that integral sign. So these components are ut, up, theta. And remember from the previous lectures that ut is composed of the part due to rotation speed and the part due to forward speed. Up has a component given by lambda. The induced velocity has a component given by beta dot, which is happening because of the flapping velocity, and then there is a component which involves mu in forward flight. Theta is given by a theta control plus r theta tw, where that is the twist. And theta control is theta 0 plus theta 1 c cosine psi plus theta 1 s sine psi, and this is the input given by the pilot. Okay, so with these we can now calculate the expression for m beta bar. So that's the integral we get, and what I have done here is that I have substituted for the expressions for ut, theta, ut, and up. And now we can put all these things together and write this integral out. Now this is something which you should do in your spare time. It is a good exercise in terms of meticulousness and integration capabilities. But actually, as far as the integration is concerned, it is quite simple because the integration is with respect to r, and r here is typically a polynomial. It is either r cube or r square and so on. So once you have done all these multiplications, you get this giant expression here, and then once all these terms have been separated out, the integral becomes relatively simple because we have expressed all these in terms of this value small r here, and you have dr here. Okay, so now this becomes a problem which is typical of calculus 1 and calculus 2 type of courses in the engineering colleges. So you do that particular integration and you get this expression here, that is the rotor flapping moment, and finally we can write m beta bar in this form. So now let's look at this carefully, because what we have done is we have put some of these expressions in brackets and we have taken some of the more physical quantities out here. So you have theta con here, you have theta tw, you have lambda, you have beta dot, and you have beta. So some of the things we see are, number one is that you have essentially periodic forcing. So you have sine psi, sine square psi terms, and therefore you are going to have pretty complicated expressions on the right hand side. You also recall that theta con is a function of sine psi and cosine psi. So you can clearly see that there will be cubic terms in terms of sine psi and such terms, and these are going to cause you higher harmonic content in the response of the system. Now this lambda would of course come from some model, could be momentum theory, could be free wake analysis or something like that. Now the interesting thing here is the presence of these motion dependent forces. So actually you have motion terms in the right hand side of this equation here, and these terms cause a lot of complexity. Actually what you should do is take them to the left hand side of the equation before you solve the equation, or you are going to encounter significant problems in their solution. So to put it in more compact form, we can go back to our rotor flapping equation and write that as beta double star plus beta equals gamma and the plethora of these terms here. Now here I have put all these moment expressions as separate terms here so that we can look more at the physics of the problem and not get bogged down by the size of the expressions and the complicated mathematics. So you see here there is a term which involves blade pitch, there is a term which involves blade twist, there is a term which is related to the inflow lambda, there is a term which involves the flapping velocity beta star, and there is a term which involves the angle of the flap. So these two should be switched. Now the interesting term is the term involving beta dot or beta star. Now this term you clearly see has a pretty large factor here, and this term essentially gives you damping, and this damping is essentially coming from the fluid mechanics aspect of the system. So this damping is pretty high for the flap mode. Now you know the flap equation which we have obtained is a periodic differential equation. You could take the motion dependent forces to the left hand side, and then you could solve this flapping equation using the harmonic balance method. So remember the harmonic balance method, you substitute beta psi is a Fourier series. You assume beta psi is beta 0 plus beta 1c cosine psi plus beta 1s sine psi and continue like that, and then you plug that on both sides of the equation, and then you essentially take the coefficients of the different terms such as the constant term, the sine psi term, the cosine psi term, the sine 2 psi term, the cosine 2 psi term, and so on, and set these all to be same on both sides, or you take all the terms on one side and put that equal to 0. Now the physical behavior of this equation could actually be studied using some stability type of techniques. So that's something which we are going to do in the next few lectures. So if you consider mu is 0, our flight condition, then the flap equation will take a much simpler form. So you can see here looking at this equation that what are the terms which are dependent on the forward speed. So if you were to set mu equal to 0, here you would get theta con by 8, here you would get theta tw by 10, here you get minus lambda by 6, here you get minus beta dot by 8, and this term is completely 0. So a large number of these terms are going to be washed out or decimated if you put mu is 0, and that is going to create a much simpler equation. So in the next couple of lectures we are going to look at that particular equation. We are going to take this motion dependent term beta dot to the left hand side and investigate the eigenvalues of that equation in the rotating frame and in the non-rotating frame. So that is very important because we can predict certain characteristics of the equations known as the flap roots and so on in the rotating and non-rotating frame, and we can extract a lot of physics from that particular model. So now this equation is worth staring at for a long time because it's going to tell you many things about the kind of forcing you get in a typical helicopter blade and in rotor dynamics in general. This forcing is periodic and motion dependent, and the periodic terms are actually quite substantial, and they are of course dependent on the forward speed, And also the big factor is lambda here, because this lambda is coming from some different model, and lambda in general is also a function of r and psi. Here we have presumed it is not a function of r and we have extracted it out, but that is a simplification we have made. So in general, if of course these things are complicated functions of r, then the integral which we have performed today has to be done numerically. So for numerical integrations, you have various rules such as the trapezoidal rule, Simpson's rule, Gauss quadrature, and so on. In those cases, you can use any of those numerical techniques to integrate this expression, and you can then solve the differential equation for rotor blade flapping in forward flight. So I will end this video here, and I will see you in my next lecture.